My name is Dirk Menzel. I'm a German professor of European Economic Integration at Pforzheim University, and I'm also the speaker of the Humboldt Regional Group and the founder of the Humboldt Regional Group in 2010. It's my pleasure to attend the 20th International Excellence Talk, which is a joint format of the International Excellence Grants and the Humboldt Regional Group Karlsruher and Pforzheim. We alternate speakers of both excellent scientific groups. The speciality about Professor Jatowt is that he is a current International Excellence Fellow and that he will start his Friedrich Wilhelm Bessel Research Award this September. Petra mentioned that already. It's a very prestigious award. That makes him already, by nature, one of the best suiting speakers for the International Excellence Talk. We're very, very happy for his willingness to share his expertise today with us, and welcome Adam in the Humboldt family as well into the Humboldt Regional Group Karlsruher. We are very proud to be part of this joint event, and I wish us all a very interesting and inspiring presentation of Professor Dr. Adam Jatowt. And it is my pleasure now to hand over to Michael Färber, Dr. Michael Färber, who will make the academic introduction of Adam. Thank you so much. Looking forward to your presentation.
Warm welcome from my side. My name is Michael Färber. I'm the host of Adam Jatowt during his stay at KIT here at the Institute AIFB. Maybe some words about himself. I think I will make it very short. He is currently a full professor at the University of Innsbruck in Austria, Adam, and he is since 2022. And he's specifically at the Digital Science Center, a specific center focusing on interdisciplinary research, I would say. He was first at the University of Tokyo and then later on at Kyoto University, two of the best Japanese universities, I would say. I met him, first of all, in 2016 when I, for the first time, had the chance to go to Japan for a short research stay. And then, we had a follow-up, basically. I had also a research stay there for 1 year in Kyoto University back then. And since then, we are collaborating, having around, what I don't remember exactly, I think it was about 15, 16 papers currently we have together already. In total, Adam published about 250 papers in total, so quite impressive. And with this, I can conclude. I'm looking forward to your talk. Thank you very much.
First of all, thank you very much for a nice and warm welcome and for coming here, despite hot weather and evening time. I know many of you are from different fields, so I hope my presentation, well, I try to make it not too difficult, so I hope you will follow it and enjoy it. Most of the time, I was in Japan doing PhD, and then had a postdoc 1 year experience, and then, well, my career, basically, assistant associate professor was at Kyoto University, and then happily coming back to Europe and with Innsbruck, and also joining here KIT, of course. This is just pictures from Innsbruck. If you have not been there, I warmly welcome you to go there and visit me also. And the university in itself, I think it's good to also share the information about the university there. It's quite old, from 17th century. This is the rectorate, the office of the administration, and also nice view here. This doesn't show. Okay, National University. We have a lot of students, but if you look where is the location, you understand that we are very much benefiting from closeness of Germany and closeness of Italy, and many students are coming from those areas. So that's something maybe especially unique about University of Innsbruck, having many foreign students. But let me now start with something very easy, some prerequisites to begin with. Things like that. No, of course, this is a joke. What I wanted to say is that I will provide you a higher level overview of my recent research. So something like this will not be there. If there is, please complain, let me know, and we'll, of course, explain more. But this is the schedule of my talk. So just a couple of slides of background first, and then I will discuss from simple solution to question answering from temporal collections, and then more advanced solution, which is called ByTime BERT, and it will be presented at the conference in Taiwan next week. And then I will also talk about our initiatives to build data sets, because in computer science, we always need data sets for supervised methods. And finally, maybe for some of you, this is especially interesting because large language models, LLMs, are now on the mind of many researchers from different fields. And we also probed or tested how they are good in our data sets, how these language models, how much they know about these things. The title of the presentation is about archival document collections, but in general, I will talk about temporal document collections. Well, the time, as everybody knows, is very important dimension also of text. You can understand the stories in a text by following timeline, the message streams of tweets, narrative documents, obviously time there is a structure binding a lot of events. And in NLP, unfortunately, which is natural language processing and also information retrieval, we feel like these aspects were not so much focused on. There were a myriad of other problems that researchers focus at, and now a bit more interest is observed in this field, but still not that much. I will later explain you more what is basically done in NLP. We can talk about two types of temporal knowledge. One is this temporal common sense knowledge. For example, the knowledge that we humans have that visiting a doctor usually is after someone is sick or break a leg or whatever, or going on holiday is taking longer than just going on vacation. That's actually wrong. I was supposed to have going on a walk here. Sorry. Going on holiday takes longer than going on vacation. Things for us obvious, but for machines, at least before large language models came, it was not obvious. And it was this kind of common sense, temporal common sense knowledge that many chatbots missed, but now it's of course getting better and better. But the second type of knowledge, and this is what I will mainly focus today, the first part about common sense knowledge, we just wrote a survey. It's another research I will skip, but I will mainly focus on factual knowledge. Something like, well, historical information that Obama was president from this and this year, or Hiroshima and Nagasaki bombings were after this attack on Pearl Harbor, right? So all this factual temporal knowledge. And I will focus on, in this presentation, on the second part of a knowledge, type of a knowledge. Temporal question answering. Just to give you a bit background on these archival document collections that we have. Well, we digitize a lot of content, like old newspapers, for example, books and other forms of analog text. Besides, we also have digitally born, obviously, text like web archive, some scientific publication collections, and so on. And altogether, these kind of data sets, collections are obviously growing over time. These archives, they are huge. We somehow forget the information from the past, focusing on the present mainly, for obvious reasons, but this information is still very important because it's our heritage, and it can provide a lot of guidance for the future and for understanding the present. So this is just an example of data that is this archival data, temporal data, over time stored in a digital form. And now, of course, the problem how to extract information from there. You can have a search engine, type some Google query, just association is too strong. Type some query and you get results. But natural language for us humans is to ask open questions against, let's say, this archival data. And that's what we want to design, that a user can come just like to a friend and ask some detailed question from the past, and the system should answer this question in an easy way, maybe giving some examples, some reasoning, also chain behind the answer, and so on. So these are the examples of questions that we actually want our systems to answer. You see, they are fairly detailed. Probably most of you will not know the answers. I show them here, or not even know probably when these events happened. These are just a sample of questions. We basically want to build a system that can answer very minor things minor events or detailed questions on major events, but very specific, where information may not be in Wikipedia, may not be even on the web, might be somewhere in the archive, and often it might be just mentioned once in some document, so there is no repetition of such information. And if you have repetition, then many systems can very well work on this repeated information. Just frequency is very helpful for us in computer science, but some minor things may only be mentioned once, or even not explicitly stated somewhere more implicit way. But we want to, of course, this is far away vision, but we want to build a system that can answer such type of questions. And the target users here are obviously for education, but also for journalists writing some papers, well, articles on the current things. They may wish to maybe ask a question about the past, find some relations, maybe starting points of certain events and so on. Plus also insurance, finance workers that want to analyze how it was in the past and better predict in the future. Well, there's a myriad of useful applications here. I just pick up some of those, but essentially, I think the most important would be historians and archivists, historians, and someone who wants to predict better the future by finding information from the past. And I mentioned already one challenge, which is lack of redundancy, that some information may not be repeated much in these collections. A second challenge is that it's over time distributed. And imagine, this is a hypothetical scenario, imagine you have a question and there are these 6 answers for the question, which are distributed over time like this, right? Let's say answer C is quite common. It appears in many documents. Answer to your question, I don't show the content of the question because just it's not relevant. What I want to focus at is how this can be distributed over time. And now the question would be, which of these is most likely? Of course, it all depends what is in these documents, what is the actual semantic of the answer. But just looking at the temporal distribution, which one you would propose that is likely to be correct, right? There could be many conflicting answers. Some people might say the most recent answer is probably the best, but not always, because if it's about detailed information on events, maybe those documents that are somewhere close to actual event happening will be correct. The most stable answer, like C over time, frequently appearing, may also not be good for fast changing events. So it's not that obvious. This situation before was when we don't know when the event happened, event behind the question. If we know that, let's say event was here, maybe our selection of answers will also be different. Maybe we say, no, the E is just too far to provide some detailed information of that event. Probably B, somewhere close to this event, may give us good answers to whatever question is about that event. Probably C not, because you see the answer was before even the event. So, well, if it's something dynamic changing, then C would not be good. So you see this temporal information, just even not looking what is the answer in itself, may give us some clues, or we can design strategies how to select the answer out of candidate answers like this. And one strategy which we actually tested is the most recent document. Is always most recent document, and I'm talking about relevant documents. All of these are, of course, relevant documents to the question. Is always most recent the good document? Actually not. We tested it. This is the first row, the document E. You see the higher number, the better, of course. For the 2 data sets, we see that this is pretty bad strategy. So not. Most oldest documents is even worse, like document F over there. Well, obviously, we still tested it because we thought, like, why not? We should also test this strategy, but pretty bad results we have. And then here are other strategies, like the one that will pick up document D, which is most common date. Like you see, all of them are at the same time happening. I mean, without this, but at least 3, let's say, the same months. Documents containing this answer. That's one strategy, and most common answer overall, which would be C, is here. But well, we have a mixture of results here. None of these strategies is perfect, and there could be many other strategies, like finding answer close to event or clustering doing and then selecting the answer. This is still ongoing work, so I don't have here final answer. I didn't test all these temporal strategies yet, at least a couple of those, excluding something that is rather obvious. Why not use always most recent relevant document to provide answer to the question? It's not always good, at least we see. But that was just initial check. What I want to now talk about is the actual system that we built. There was work done with Michael together. It was 3 years ago, so before all these large language models came, or at least became popular. That's why it's rather simple system, but it's easy to understand, I hope. A system which takes the collection that we were working on was this New York Times collection over 20 years, close to 2 million articles, and comes a question from the user. It could be a very detailed question. Obviously, the system, we call it KANA, question answering in use archives, supposed to give the correct answer. So how we solve it before fancy deep learning technologies were popular. So we took the question like this one, we extracted most important words from it, omitting something like as or of, which don't have much semantics, much meaning, can be safely dropped. We sent these queries, well, one query, of course, but keywords against indexed collection of news articles, these 2 million news articles nearly, and we gathered top N results. This could be 1,000 most relevant documents to this query. Of course, we don't know what is the answer in these documents, what is the correct answer. It's still a bunch of candidate documents first. But then we look into distribution over time of publication dates of these documents, right? You see there is no year here mentioned, no temporal information, but since each news article has timestamp, we can portray their frequency, and let's say there are 1,000 of those, we can portray them over time, see this temporal distribution, and basically, based on this distribution, we can rewrite these documents to have perhaps smaller, more relevant, according to our system, and hopefully really more relevant documents that will provide a good answer, right? So let's see, well, then we can remove many documents which are somehow we think are not good, and just focus on the smaller set of K documents. Then these documents could be later taking the question initially just processed using standard lookup, well, not a lookup, but standard question answering system, DRQA at that time, to extract a span of text that should be providing a correct answer to this question. But what is important is that now we have the smaller set of documents rather than a lot of relevant ones, and then just we look what is the most common answer and provide the answer here. So that was the whole system, and as you can see, it's not supervised. We have many simple steps, and it was still working quite well, but later we improved it, which I will also talk about further on. Let's focus on this particular module here to look into the distribution of results and actually to find the time of this question. We don't know when this event happened. There's no date here, but looking at the distribution, we may try to find when this event happened. And here is an example. Levinsky told whom about her relationship with President Clinton. You see this black line here, actually the dotted line. The black line is a moving average. You see the dotted line, which shows, dotted dark line, which shows the distribution of articles. Clearly here there is just one period where there was a burst of articles. We can have a cutoff here line and do a burst detection algorithm, which is, there are many of those, and say, okay, the event behind this question, even though there is no date here, is somewhere here, right? And this will be very important information for us for further document rerun this time period. But of course, situation is not always that simple. You have a more tricky question like this one, that might be about Japan actually, where you have at least 2 peaks, of course, depending on parameters of burst detection, but let's say there are 2 peaks. And so 2 time periods, which could be with some probability, probably higher or smaller, when the event actually happened behind this question. So once we have this question time estimated, as you have seen by burst detection, we can use it for re-ranking documents. And again, this is very simple technique. Suppose for the question I estimated the event happened here, which of these two documents you would say is more likely to provide answer to this question? Well, you would say that the A, because it's just closer, right? So more relevant. Not even looking at the text, just looking at the timestamp of these documents. Okay, this is one type of score. Another type of score is that if we look at, there's a lot of words in the document, obviously, but if we just look at temporal expressions, we might see that these two are falling into our question time scope when the event happens. So maybe DB will be now more relevant. The score of DB should be higher than DA. And then we combine these two, content time score and publication time score, together with a bit more here things like kernel density estimation, because rather than one period, which is in a simple way shown here, we might have several time periods when the event might happen with probabilities. So there's a bit more here in mathematics, but I will not bother you with this as I promised. And then we aggregate it all just to, well, re-rank these end documents just to pick up the good ones, maybe only 50 out of initial 1,000, and then extract all the candidate answers, find the most common, and that's it. That's a very simple system, as you can see. We tested it on this New York Times corpus, as I mentioned. We made 1,000 questions manually, looking at Wikipedia or borrowing from some websites like this history, fun, trivia, quizzes, and so on, a combination of different sources. And then we found our system. I will not maybe explain so much detail these metrics, but exact match would mean exactly what the system returns is what the ground truth is, the actual answer is. So the higher the better. F1 here is a bit more relaxed version that if some words are not returned by the system, it is still okay if certain words are, right? You might say President Bill Clinton is the true answer, but my system returned just Clinton, right? Or President Clinton. And it's partially good. We should consider it. So this is a bit more relaxed version. This one is very strict. So you see, it's better than some baselines, better than baselines which do not have one of those temporal scores, which are explained. So they are useful, these scores, but still much room for improvement. And then we thought, like, let's go to more general approach by providing time-aware embeddings. And maybe some of you may not know what are these embeddings. You can consider it's like a vector that represents meaning of the word. Each word would have a vector. And then if you position these vectors, let's say on two-dimensional space, you might see things that the similar objects are close to each other. Things like chair and table should be close to each other, right? But on the other hand, car and democracy far away because the meaning is so different of those. And that's the standard embeddings that we have. Typically, this is still being used. It's BERT, which is like a hammer now for NLP. You can do many things with it. It's basically vectorizing every word or a sentence, and then machine may operate on vectors, no longer on words. But there were some variants which were interesting for us from the viewpoint what we want to do, like incorporate time into this BERT. Variants like SpanBERT and SentiLerge. So basically, this is focus on not a word, but on the span for pre-training task. And this was focused on sentiment words like good, happy, cheerful, or bad. So that the system will, when constructing these word embeddings, these vectors, will pay more attention to sentiment words than the other random words. And then the final embeddings, final vectors will be much more useful for whatever you do with sentiment. Right, so that was this idea, modification of BERT, and we also thought why not to apply it to use for time-aware embeddings, and we proposed two approaches here, two pre-training tasks. One is called time-aware mask language modeling, the other documentating. Just not to bother you too much with the details, the main idea behind the first one was that we, this is first screen, sorry. We masked not just any random words and forcing a system to predict these words, but we also masked, I think there was a percentage of 30% of time expressions we masked, like last December, yesterday not, this 1997 not, but many of these temporal expressions we actually masked, forcing the system to predict them. And during the prediction, the embeddings, the vectors will be constructed. They will be more robust against temporal factual knowledge than any random word we would ask. So that was the first task. The second task was document dating. Here is the actual document date with a monthly granularity, and we force the system during pre-training to, looking into the text is very short here, guess what is the timestamp of this text, right? So, and again, the word embeddings were constructed with this particular pre-training task, so more robust to understand the temporality. We also have another task which didn't work that well, but I will still discuss it. It was influenced by the system that actually swapped name entities in a document, randomly swapped one name entity with the other, forcing again vectorizer, the system that builds vectors, yes, plain terms, to pay attention especially to name entities. We did the same with temporal expressions. So we took 50% of temporal expressions and we replaced them, just like you see the case of December, now replaced with November, or 1993 replaced with 2003. We did this corruption of the text, forcing the model now to guess which of the temporal expressions were corrupted and which not, given all the text, right? Which is a lot of reasoning. Sometimes humans may actually find these problems. Machine has advantage of looking at millions of documents, so finding some patterns, and you know, it's trying best to represent meaning of each word during learning how to uncover these swapping temporal expressions. But actually, this didn't work so well, so we didn't incorporate it into final BERT model. Sorry for so many results, but we tested on event dating. If you have a description of event, tell me when this event happened. You have a Battle of Stalingrad, you say 42 or something. You have a, I don't know, Crimea war against some other date. That was one task, and our system is the last one, was the best. This one was document timestamping. I give you a random document, news article, tell me when it was published. Again, we performed very well, and this is this replacement pre-training task that didn't work so well. We have sentence dating, and what is most important for us in this context, question answering. The first line is the previous system, the very simple that I introduced. Now we incorporated this vector embeddings by time word. We call it, you may guess why there is by, because there are two types of time, timestamp and temporal expression in the text. And well, it was performing better, squeezing a bit more points for us. But still, at that time, we thought like, we don't have a big data set. What we just tested on was 1,000 questions. That's not enough for training any big complex neural networks. So then in another research, we thought like how to generate a large data set of questions and answers. If we have those, of course, they are about archives. If we have those, then we can train some complex model. But how can you generate 500,000, because that's what we had, question-answer pairs about basically this period? Well, we don't have that resources to ask and not that many friends to ask also to do it. So we did automatic way. These are the questions, examples that we generated. Basically, we use a question generation tool to take some random news article, generate a question from certain paragraph, and also we knew what is the answer because the answer was part of the paragraph. We generated those over time. Here is the most common words like what, who, when, where, so good distribution over different types of questions. Of course, these are automatic, but we had many stages of filtering, removing bad, too long, too short questions, or questions where you don't know what is really asked, like where he was working, right? You will not answer because we don't know who is he without looking at the context. So we had many stages of removal. Initially, we had 6 million questions that we went down to a smaller set, I think more than 500,000. But then we noticed there is another problem in those questions. If you look at the red ones, like what did Syrians want to end? Which country is the current US policy? Who was the senator of West Virginia? They seem like you can answer them, but if you consider this is 20 years time period, there could be actually several answers correct there were probably a couple of senators over 20 years of West Virginia. Which one we really ask about, right? So there is this temporal ambiguity, and we wanted to drop this kind of questions and retain like those ones which are so specific, probably never happened that exactly 20,000 American troops were sent exactly to Bosnia. So, well, that's probably, good question. We wanted to remove those ambiguous ones and retain good ones. Well, looking at 500,000 of candidate questions, it's not feasible. So again, with the automatic solution, we had some small data set of questions we annotated, 5,000 over, which we annotated ambiguous, like this one, or non-ambiguous, like this one. Then we train a system to recognize between these two, and we run it over our candidate questions to remove those ambiguous questions. Of course, accuracy is 81%, so it was never perfect, but we had a better data set. And now with Michael, actually, we are working on building another data set using Wikipedia, which we think will be more correct. And upon brief checking, we find that it's actually more correct to make also these temporal questions. And we hope to have a couple of millions of those because it's again automatic way. You have examples here, like who was Prime Minister of Lithuania during Lithuanian European Union membership referendum. Another, which is comparison question between two events. Did this tornado was more deadly or more fast in terms of wind speed than another hurricane, or this accident had more casualties than the other accident? So it's two events that we need to compare. Another, you have comparison also, I think, but comparison in the sense that there is some event, and after this event who was the governor, and then the counting questions, like in SQL, you would have the question from database, how many times there was some event from this and this period, event like some massacre in Canada, right? So you see, these are rather complex questions than the ones we had before, and we could generate them from Wikipedia using basically almost hundreds of SparkQL queries crafted especially for those, and most of them are correct. And we'll have a large data set. Still work is ongoing for further training the systems. So this brings me to the last part of my presentation, which is about large language models, LLMs. It is still under review work with some colleagues done. And well, this slide shows the genealogical tree of large language models. There are many of those. This is 2003. It's actually from a survey of these models. And many of those, we could not test many, but we picked up two. One is from the family of from the family of llama models, alpaca, 7 million parameters. This number means how powerful is the language model, the more the better, obviously. And then text Da Vinci, which is from GPT-3 family that has 175 billion parameters and should have a lot of knowledge because it was trained on huge amount of data, like this one, Wikipedia, Common Crawl, which is part of the web, scientific papers from Archive, Stack Exchange, and so on. These two models were trained on those data, and we wanted to basically test how much these models know about history, especially if I ask some detailed questions, minor questions, and some other tricky things we tested with these models. The data set that we used was this first data set that I mentioned, 1,000 questions, then Archival QA, which is just introduced, 500,000 questions. The first one was about major events, the Archival QA, very detailed questions, and then there was also Temp Llama made by Google researchers that are basically knowledge graph triples for this time period, something like Cristiano Ronaldo played for which team in 2020. And the other two questions are from the above two data sets. So we had, well, 80,000, no more, 120,000 of this kind of questions with answers, of course, already given. And now we wanted to test large language models like ChatGPT, not exactly ChatGPT, but like how well they can answer those questions, right? And first, we just did a very general pass over all our 3 data sets. These are these results, exact match whether the answer is exactly how it should be correctly, a more relaxed version of it, and contains means like whether the answer is contained in all this text returned by ChatGPT large language models. Sometimes they are not strict to the point, sometimes they something longer. Basically, the larger, the better results. But they are very low, and we already see, especially on Archival QA, as I said, it's about minor things from the past, and we can compare these numbers, which I repeat here for the two large language models, against models that were actually trained on this archive, on the New York Times archive, not large language, just more simpler versions, and you see the numbers are much better, which means that you may still need this specified model trained on archival collection, dedicated to it, because these generic models trained on the web, actually not on the web, also books and some other corpora, but in general content, they are not that good in answering the questions. And you can see some answers here by, this is a grand truth answer, but the ChatGPT and Alpaca, you see they are not always the same. Right? Actually, these examples, they are wrong. The nuclear plant of which city was closed down completely in December 2000. Chernobyl is the answer, but ChatGPT says Mihama in Japan. I don't know if it was really closed at all. Might be some hallucination. We know this is the problem of large language models in general. So anyway, what we can conclude is that performance is rather poor, especially compared to other types of questions. We need some maybe more dedicated solutions for that. And next step, we analyzed type of errors, taking 100 wrongly answered questions for each of the model and just looking, what is the type of error? What was the problem? Well, there was no answer quite common, especially in this second model, Da Vinci model, but also plausible answer was quite common, which means that the model was quite correct, close to correct, but not precisely correct, right? Maybe he said, well, Obama instead of Bush or Clinton instead of Bush, you know, somewhere close there, but not precise. So that means, yeah, there's a hope there. There were some other types of errors where I would skip them. And actually, yes, this is one type of error, we call it time shift, that not the entity that we ask about is the answer, but the previous or the next one. It's kind of, the model is a bit confused over time. And then we also tested how accuracy, how good is if we look into each year of the data set. Maybe it's not very conclusive, but we notice a little bit improvement over time if we look into this trend, which means maybe more recent past is easier for the models to answer, because on the web you probably have more information on the recent past than on the deep past. But we have to remember this is very short, so we need to test it. And also we notice this drop here, which we attribute to something very obvious, that these models were basically trained until certain period, right? Until 2020 or 18. So they don't see the newer data, and they may not know about more recent things like, I don't know, the war even with Ukraine, right? Because they just didn't look into this data. They were trained on some until some point and stopped. So this could be the reason. Of course, we need to test more for this drop of accuracy for the most recent questions. Okay, but what we tested next is something that maybe humans are also not good at. We substituted these years in the questions into relative ones. So basically, instead of giving concrete year, we just make it harder for the model 3 years ago. But we needed to know what is the year for the model, right? So we asked the model, what year do we have now? And the answer was always 2021, because the model was trained until 2021. So then, considering the now year is 2021, we came up with this number, because this is, and just substituted every question with this relative years, and tested how well the model is now for this kind of questions. And these kind of questions are here in a green color compared to the absolute ones like this in a red color. Here, yeah, the absolute are green and yellow are this. So basically this performance drop. The model is more confused now, 35% up. the confusion happens when you ask this kind of question rather than this, right? Where human would be probably even more confused trying to, do calculations. Anyway, average user may ask this or that question, right? So the model in principle should be robust for both. Then we did something else, like we did a randomization of these years, right? So who refused the post of Prime Minister of India in this actual good year, but we now shifted completely different date to see if the models will still recover or not. And you see that there's a performance drop. We found that it's about 31 to 40% performance drop, which means that these years are considered by the model, right, to some extent. Maybe they are not the best in reasoning over time, but if you corrupt it completely, the models, drop, the accuracy will drop. So that means, well, we can understand there is some temporal reasoning going on. We even further went more into this corruption, changing it to somewhere close, then farther until very far away, and just to see what will be the results. If it's a very big corruption or just a little bit, impreciseness in the time, and then we observe this kind of gradual drop in accuracy, whether you have absolute or you might have even, 3 years ago, 4 years ago, so relative time expressions, both of them are gradually dropping. Basically, the conclusion is the more you do this corruption, the more error you introduce, the worse will be the results, which maybe is rather expected. Then which questions are the most difficult, because we had different questions of how, which, when, and so on. For the model, these kind of historical questions, and we found that when question especially is difficult, the accuracy is very small compared to other types of questions. Then next one, we look into question length. So how long you have a question. This is in characters, so 100 characters versus very short question like this 2040. Again, we tested absolute but randomized and absolute correct. And the conclusion is that the performance is increasing where you have a longer question, but only in the case of corrupted temporal expressions. So basically, there is more text given, more context given, and there is this wrong here, but this year now becomes less and less important because you just give more context to the model, so the model still can recover better, even you corrupted temporal expression. And then we attempt to categorize this kind of different errors, because once you, like in a science, distinguish and name things, then it's easier to fight against them and make dedicated solutions. So one problem would be, we think, popularity bias. So some entity may be just too popular for certain event, and then this event is so popular in the data set that it's overshadowing whatever else you ask about this entity, and always the answer will be just this major point that you remember, well, the model remembers. That's a popularity bias. Temporal inertia is something that basically the model stopped being. The training went on, the new information came, but the previous information was so popular still that this new information is not frequent in a data set enough to make the shift of the model, right? So if we say that, as an example here, Tom Brady played for which team 2020, the model should know the correct answer, which is Tampa Bay, but it's still too short time that this person played there. There is still not too many documents mentioning this new position, new team. So the model by inertia is still, giving the wrong previous answer. And then something like temporal shift. So the entity, the previous or the following entity is confused with the actual entity, and the problem with referencing. If I ask something like, what stage did Tuscany join 162 years ago? That this confuses the model, and the problem comes from that. This is not exhaustive list of problems. There probably will be many. We just started this work, but we aim in the future to maybe look more closer into these problems and design, as the future work also indicates here, design a new prompting style, new way you can write the prompt, maybe time-aware prompting style, maybe integrate temporal knowledge base with large language models, because knowledge base is usually correct. most of the time, and very specific. There are some ways to do it. And then further mapping these blind spots in large language models. But that's for the future work. Just to conclude the talk, what I show you were this simple approach to temporal questions, more recent one based on embeddings that are focusing on the time, especially during the construction. Then I talk about two data sets. One we already did, and the other one is now being done using Wikipedia and SparkQL queries. We hope for a couple of millions of question and answers. The first one still have many problems, errors, but the second one should be very, very precise. And then we want more to probe capabilities of large language models when it comes to temporal reasoning, information about the history, and so on. So we finish here and happy to answer questions.